Homework 5, problem 10, find the polarization alpha for an atom where the electron cloud is treated as a uniformly charged sphere. We've done this example in class, but it's good always to do things multiple times, make sure you understand. The idea that we're looking for here is we want the force on this positive charge to be the same in both situations. So the total force, not the same, to be 0. We don't want it to move. We want this to be a static picture. And so that says that the force due to the applied electric field must be equal and opposite in sign to the force due to the charge cloud. So the force due to the electric field due to this charge cloud must be equal and opposite in sign to the force due to the applied electric field. The force due to both of these is just the Lorentz force. It's the charge, which in this case is Ze times the applied electric field, should equal to minus Ze times the electric field from the charge cloud. So these cancel, and we now get this. So the trick here is we need to find what the electric field from the charge cloud is as a function of this little d. Okay. That's actually really easy. We have a symmetric system here, and so we can use Gauss's law. Okay, draw a sphere. We know that the electric field must point radially outward. The electric field due to the spherical charge distribution must point radially outward. And Gauss's law says, like the statement of Gauss's law, right, is that the integral, the flux through the surface, d2x in hat dot electric field epsilon naught, must equal the volume integral of the charge density, integral d3x v of the surface delta v of the charge density, which in this case is just, what is the charge density? This is Z minus Ze over 4 pi capital R cubed, 4/3 pi capital R cubed. Okay, plugging this in, we know that the electric field points radially, so this will just be 4 pi d squared. And on this side, we're going to get 4/3 pi d cubed times this expression that we have, minus Ze over 4 pi. And what we find, this is times electric field, right? And what we're going to find is that the electric field due to the charge cloud, these 4/3 pi's will cancel, and we're going to divide by 4 pi. We have an epsilon naught, so we're going to have minus Ze over 4 pi epsilon naught r cubed, 4 pi epsilon naught r cubed times d, like that. Now, so plugging this in to this expression up here, we find that the applied electric field is equal to, this minus is going to cancel with that minus, is equal to Ze times d vector over 4 pi epsilon naught. And if I'm really observant, I'll notice that this is equal to my dipole moment P. And so that gives, solving for the dipole moment P, the dipole moment P is equal to 4 pi epsilon naught. There's an r cubed minus r cubed times the applied electric field. And from this, we recognize what the polarization is. It's this expression that multiplies that. And so from this, we have that the polarization is 4 pi epsilon naught times r cubed. Notice something a little bit interesting here. The polarization did not depend upon the charge of the atom, and so this would be the same for any spherically symmetric atom. So it should be the same for a hydrogen atom in its ground state as for a helium atom in its ground state, which is a little bit interesting. I don't know if that's true or not, but that's what this model is suggesting. Kind of interesting.